I now call to order the Society's 2,435th meeting in the 149th year since its founding on March 13th, 1871. Good evening, everyone, and welcome to PSW Science's Spring 2021 meeting and lecture series. Because of COVID-19, the Society is bringing this meeting to you via Zoom from locations all around the globe, rather than our usual home, the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. This evening's lecture will be about the Parker Solar Probe, now giving us our closest observations ever of the sun. Our speaker is Nicola Fox, who worked on Parker for many years and is now NASA Director of the Division of Heliophysics. I'm Larry Milstein, President and Program Director of PSW Science, one of the oldest scientific societies of Washington, D.C., founded in 1871 as the Philosophical Society of Washington, to provide a forum to exchange scientific ideas, further scientific understanding, and encourage scientific inquiry. This lecture is being recorded and will be posted to the PSW Science YouTube channel, where it will join over 150 other recordings of PSW Science lectures. We invite you to explore these presentations and to become a member of PSW, which you can do through the PSW Science website, www.pswscience.org. The Society is grateful for the sponsorships of the 2020-2021 lecture series by the Policy Studies Organization in cooperation with the American Public University, and by a donor who asked to remain anonymous. Our thanks to all of our sponsors. Before we turn to the lecture, in keeping with the traditions of the Society, we welcome new members and will read the minutes of the previous meeting and the summary of the previous meeting's lecture. I am pleased to announce that the following new members have been elected to the Society. Alain Lanier, instructional designer with General Dynamics Information Technology, interested in exoplanets, who learned at PSW Science from an email he received. Faraz Assam, an information tech with the Iraqi embassy, interested in computer science, quantum computing, the Big Bang, and dark matter, who learned of PSW Science on the web. Avi Loeb, astronomer at Harvard University, and our previous speaker, a man of many interests, who learned of PSW from our invitation to him to speak to us. And Nicola Fox, our speaker tonight, who learned of PSW through our invitation to her to speak tonight. And some of her interests will be clear from her lecture. We welcome them all to membership. Membership is a most important pillar of the Society. I encourage everyone with an interest in science to become a member of PSW. It's easy to do using the PSW Science website, www.pswscience.org. PSW is a 501c3 charitable education and professional organization. Dues payments and other donations to PSW Science are tax deductible. Recording Secretary James Heelan will now read the minutes of the 2,434th meeting and the lecture by Avi Loeb. A video of the lecture is available for everyone without charge on the PSW Science YouTube channel, the PSW Science video channel, and it can be accessed directly from the PSW Science website, www.pswscience.org. It appears that James is not available due to a fire alarm and the requisite requirement that he leave the building. And so instead of James, I am going to read the minutes that he kindly provided. At the Cosmos Club in Washington, D.C., April 20, 2018. Oh, pardon me. On February 5th, 2021, by Zoom video conference broadcast on the PSW Science YouTube channel, President Larry Milstein called the 2,434th meeting of the Society to order at 8:02 p.m. Eastern Standard Time. He then introduced the speaker for the evening, Avi Loeb, Baird Professor of Science at Harvard University and Director of the Institute for Theory and Computation at the Harvard-Smithsonian Center for Astrophysics. His lecture was titled, "The Search for Extraterrestrial Life. Are we the sharpest cookies in the cookie jar?" Loeb began by asking, are we alone? He encouraged humanity to embrace a cosmic modesty. Given that current data suggests approximately half of all star-like stars in the observable universe host an Earth-sized planet in the habitable zone, Earth is a single grain of sand on an enormous beach. Rather than assume humanity is unique, Loeb advocates that we assume the existence of other technologically advanced life and search for its signatures. In 2015, entrepreneur Yuri Milner asked Loeb to advise him on an initiative to visit the nearest star system within our lifetime. After months of consideration, Loeb agreed to the invitation and began working on Project Starshot, a proposed mission to send a vehicle to Proxima Centauri, 4 light-years away. Now named Breakthrough Starshot, the initiative aims to launch a spacecraft that will reach 1/5 light speed and take a picture of Proxima Centauri's potentially habitable planet, Proxima b. From launch to the receipt of a picture of Proxima b back on Earth will take approximately 24 years. Loeb proposes the Starshot spacecraft be a light sail mounted with 1 gram of camera, navigation, and communication instruments. The light sail would weigh approximately 1 gram, span several meters, and be accelerated to 1/5 light speed by a 100 gigawatt ground-based laser. Feasibility studies are currently underway regarding the laser optics, the design of the sail, and the challenge of communicating across 4 light years. In addition to crossing the interstellar street, so to speak, to look for advanced life on other worlds, Loeb said we should not assume that every rock that passes through our backyard is just a rock. On October 19, 2017, scientists at Pan-STARRS in Hawaii identified the first interstellar object in the solar system that has been observed. They named it Oumuamua. Because Oumuamua is only several hundred feet long, Earth-based telescopes could not resolve it. Scientists tracked the object's trajectory and observed that it moved from the local standard of rest to the south of the elliptic plane of the solar system over an almost 2-month period. By observing fluctuations in the light reflected by the object, scientists determined that Oumuamua was a flat, pancake-shaped object tumbling through space. The object's deviation from Keplerian orbit suggests that Oumuamua was pushed. But the Spitzer Space Telescope did not observe any infrared energy or outgassing from the objects. Popular suggestions to explain the object include that it is a porous structure of extremely low density, that it is a fragment from tidal disruption, and that it is composed of molecular hydrogen. But none of these suggestions, Loeb said, is consistent with all of the object's observed characteristics. Loeb asked us to consider that Oumuamua was artificially created and pushed, so to speak, by an alien civilization. In support of his point, Loeb described how, in September 2020, Pan-STARRS discovered an unusual asteroid exhibiting similar characteristics to those of Oumuamua, whose trajectory could only be explained by a push. Ironically, the object was ultimately revealed as a rocket booster ejected into space in 1966 by the intelligent civilization on Earth. Loeb said the story of the rocket lends credibility to the notion that artificial objects with a large surface-to-mass ratio can be distinguished from naturally made rocks based on their excess push away from the sun without a cometary tail. A second interstellar object was discovered on August 30th, 2019. This object looked like a comet. To Loeb, the mundane nature of the second object makes Oumuamua even more unusual. In conclusion, Loeb said, humanity needs to be prepared for its next encounter with potential evidence of alien life and should examine more than radio signals. He recommended we broaden our scope and search for evidence in physical objects like Oumuamua. During the question and answer period, Dick Garwin, physicist, asked a question about whether the light sail would have to be extremely flat in order to avoid being torn by differences in the pressure from the 100 gigawatt laser beam. Loeb said that this was under study, but he thought that it would not be a problem. But subsequently, the two agreed to pursue the matter further offline. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 9:40 p.m., President Milstein adjourned the meeting. Temperature in Washington, D.C., 6 degrees Celsius. Weather, partly cloudy. Concurrent viewers of the Zoom and YouTube live stream, 152. And views on the PSW Science YouTube and Vimeo channels, 553. Respectfully submitted, James Hewlin, Recording Secretary. Thank you, James. The minutes will be posted to the website in due course. Please send any corrections or comments on the minutes to Corresponding Secretary Robin Taylor at correspondingsec@pswscience.org. We now turn to tonight's lecture. It's my pleasure to introduce tonight's speaker, Nicola Fox. Nikki is the Heliophysics Division Director in the Science Mission Directorate at NASA headquarters in Washington, D.C. Previously, she served as project scientist for the Parker Space Probe and as chief scientist for heliophysics at the Johns Hopkins Applied Physics Laboratory. Nikki is an author on numerous scientific publications, and she speaks frequently on science, both to the public and at scientific gatherings. Among other honors and awards, she is the recipient of numerous NASA awards for outstanding performance. Nikki earned a BS in physics and a PhD in space plasma physics at Imperial College, London. She also earned an MS in telematics at the University of Surrey, United Kingdom. All questions will be fielded in a Q&A session after the lecture. Nikki, the screen is yours.
So thank you so much for inviting me. It's a pleasure to be with you this evening. As I'm sure all of your speakers for the last year have said, I do wish it was in person and not via Zoom, but it is very nice to be able to speak with you anyway. So yes, I'm going to talk to you about a couple of missions, but really focusing on the Parker Solar Probe, humanity's first visit to a star. And that's a mission that's very near and dear to my heart. I spent a long time working on that mission from just after the instruments were selected through to it clearing the launch pad. And then I started down at NASA headquarters just a couple of weeks after that. So delighted to tell you about Parker and also all of the things that we have in the Heliophysics portfolio right now. But I'll start off with just number one, they're just spectacular views of our star, but really close-up views of all of the activity that goes on our star. We are very lucky. We have this star kind of in our backyard. And so even though it's difficult to get to actually go up and really physically visit the star, we've been able to look at the sun at all different wavelengths and in many different ways, also going in as far as just inside the planet Mercury, the orbit of the planet Mercury. And so we've done a lot of studying, but what we're going to talk about today really represents the breakthrough that can only come by actually going up and physically visiting the star. But these are just very beautiful images of some of the activity that we see, these very interesting explosions, little mini explosions. You see sort of loops of magnetic field that constrains plasma, kind of getting very active, stretching, and often breaking. And of course, when that breaks, it will send billions of tons of this coronal material out into the interplanetary space, carried in the solar wind. So if we take a look at the planet, you can see, and my movie never plays properly, so I'll just sort of talk you through it. But you can see our planet there kind of being shielded from these particles that are coming from the solar wind. Because the Earth has a very strong magnetic field, it kind of stretches out and makes the solar wind this continual river of plasma coming from the star. It makes that sort of divert around the Earth, protecting us from a lot of the very nasty radiation that's coming in. Some of it, of course, does come in and causes activity for us here at Earth, but a lot of it is just we are sort of protected by our magnetosphere. But if we move away from the Earth over towards the sun, and we can look down on the pole from the sort of over the north pole of the sun. And what you can see there is this atmosphere, this sort of hazy atmosphere that you see during a total solar eclipse is spiraling continually away from the sun. So that is what gives rise to the solar wind. That's what we see interacting with the Earth's magnetosphere. And then if we go all the way to the other edge of our solar system, when we're looking now from the side, you can see that the solar wind kind of forms a sort of protective cocoon for our whole solar system as it's orbiting around in the spiral arm of the Milky Way. And so it's the sun itself is not only causing dynamics for us here at Earth, but it's also creating kind of protective cavity for all of the planets as we orbit around. So lots of good stuff happening with our star. So we realized, obviously, that the sun has a profound effect on what we see here at Earth, but it was a relatively recent discovery that they were so closely linked. So in 1859, a British astronomer, Richard Carrington, was sketching sunspots. He was looking through his brass telescope and sketching what he could see. And so you can see there a particularly large sunspot group that he'd been watching for a number of days as it was rotating around on the disk. While he was sketching it, he saw kind of bright white flashes of light. He said they looked like fireballs on the sun's surface. He rushed off to get a colleague to say, golly, look at what I've seen. And by the time he got back, the fireballs had disappeared. But just a few hours after he had seen this happen, of course, it was the first observation of a solar flare. A few hours later, compass needles at Earth began to spin. The aurora was seen down at very low latitudes down towards the equator. And the telegraph system in the US sparks flew from the wires and the whole system went down for about 4 days. And so that was when that was realized that there was this profound effect between what was happening on the sun and what was seen here at Earth. So we know that space weather. We call it space weather when we see these impacts here at Earth, and we know that it is very key to having effects on our technology. In March of 1989, there was a Carrington-like event. So we sort of mark everything. We use that Carrington event as a benchmark. And here you can see a sort of dramatization or an animation of the lights all turning out in the Hydro-Quebec region of Canada and into the northern US. And that were widespread power outages were caused by this extreme event. Very, very intense aurora was seen overhead of the power grids as the whole system started to collapse. Many people were without power for a number of days, but fortunately it was a fairly localized event and it only hit that part of the country. We don't have to wait 150 years for such big events. In July of 2012, the most intense solar storm was observed in the last 150 years. Now, it went off the side of the sun. It actually impacted one of our Stereo spacecraft, and you can see there the images that Stereo was able to capture of the event leaving the sun. Stereo also, in addition to having images on there, also has some in situ instruments, and so they were able to measure the size of the event. So we were then able to model what the impact would have been had it hit the Earth. And so had it happened just 1 week earlier, it would have been right in that target region where the sun and the Earth are totally aligned, and that event would have come directly to us here at Earth. The models predicted that there would have been very big effects to power grids, and various other technologies would have been affected, with a price tag of about $2 trillion lost to us all. So very, very important for us to understand what is going on in our star. So the way we do that in the Heliophysics division is we fly our Heliophysics System Observatory. And you can see here a nice graphic showing all of the missions that we currently have in various different phases. I'm just going to hit the button again, and we'll add all of the recent selections that we made in the last year. So while 2020 was an incredibly trying year for everybody, Heliophysics actually experienced a year of growth, and we selected a lot of missions, taking us to 20 operating missions with a total of 27 spacecraft in that constellation, 11 missions in formulation, and we also have a further 9 missions that are under study. So a ton of really exciting things happening in Heliophysics. And you can see the way the positioning of all of the different observatories really allows us to look from close up to the sun with Parker Solar Probe, Solar Orbiter, the sister mission, which we actually launched in 2020, right before the pandemic really took hold. That mission is out in the solar wind, currently doing coordinated measurements with Parker Solar Probe, and with over the time of the course of the mission, that spacecraft will come out of the ecliptic plane and will allow us to be able to actually look down on the poles of the sun, as well as taking some in situ measurements of the plasma coming from the sun. We have a fleet of spacecraft that sit at the L1 point, so the Lagrange point, about 1 million miles upstream of the Earth. And they're kind of like our early warning systems. They're telling us what is coming towards us in the solar wind. So they really help us to predict the space weather. All of the other spacecraft you see are located in the Earth's magnetosphere or ionosphere thermosphere system. And so they're really looking at all of the impacts of what is coming to us in the solar wind. And then last but certainly not least, my Voyager spacecraft, 2 spacecraft that have left the protective bubble of the heliosphere and are out in interstellar space. And so we really do study in heliophysics everything from the interior of the sun all the way out to the fragile boundary between where space weather or solar wind stops and interstellar space starts. And so we really wanted to, we have all these to allow us to look at some long-standing mysteries of solar physics. And the first one is no surprise to anyone. It's the big mystery for us, which is why is the corona so much hotter than the surface of the sun? And if you look at this movie playing over, it'll start again in a moment with the sun's surface at about 6,000 degrees. And then as we step further and further away from the sun's surface out into the corona, we see the big surprise, which is there's a temperature inversion. And as we get away from the star, the temperature actually increases until it gets to about 300 times hotter than the surface of the sun. That is a mystery that has plagued scientists for decades and decades. The second one is, where does the solar wind originate and how is it accelerated? And so as the solar wind leaves, as the atmosphere of the star rather leaves the sun, it's kind of continually accelerated. It isn't just a simple, you put energy in close to the sun and then it slows down adiabatically as it's moving away from the star. It's actually got almost like a continual acceleration process. So it's actually moving faster than you would predict. So we really want to understand where it originates and how it gets continually accelerated. And the last of the main mysteries is, how are solar energetic particles accelerated and transported? So these are the high energy particles that are associated with transients in the solar wind. And you can see one there being accelerated at the front edge of a big coronal mass ejection. So they're associated with transients, things like flares, shocks, and large coronal mass ejections, sending these very high energy particles straight towards Earth and causing a lot of space weather impacts. So they are the sort of three of our very long-standing mysteries. And so Parker Solar Probe, of course, is steeped in history, and it goes back to the dawn of the space age. You can see in 1958, James Van Allen there chairing the Simpson Committee with John Simpson, and of course, launching Explorer 1, which allowed us to discover that space was not empty. It was actually very interesting. Around the same time as Explorer 1 launched, a young scientist, Eugene Parker, published a very seminal paper. And in it, he predicted that the solar wind would indeed leave, it would break away from the giant pull of the star and bathe all of the planets, really forming this cavity that we actually have now seen today. He did it, as he likes to tell me, he just did it by solving 6 fairly simple equations. And at this point, his definition of simple equation might be different to other people's definition of simple, but he solved all of the equations of matter, and he came up with a number of different solution curves. Some of them were just not possible because of just basic physics. And there was one that was his solar wind curve that really predicted we would see this acceleration close to where we see the heating. The paper was not well received. In fact, of the reviewers, he had one reviewer who said, you know, if you're going to publish in this area of science, you might want to visit a library first. And then he likes to sort of laugh and tell me that that's the nice review. But fortunately, the editor thought, well, wow, this is a really controversial paper, we should publish it. And so it was in 1958, it was published, and it led to the inclusion of a solar probe type mission in the Simpson Committee report. So the Simpson Committee was convened to really give advice and guidance to the newly formed agencies. So NASA, obviously, also the National Science Foundation and the DoD. What do we want to do with this newfound thing called space? What are these really big missions that require a national agency, not just, you know, a single institution that could do them? And they proposed 14 missions. Of those 14, the only one that had not flown at the time of the launch of Solar Probe was indeed Solar Probe, because it's a hard mission and we have to wait a long time for technology to really catch up with our dreams, our hopes and desires as scientists. And so Gene's paper was a real sort of deal breaker. It was the real thing, the real push that made this Solar Probe be one of these key missions. But of course, we've had to wait a long time for this mission to come to fruition. And so really it is the long-awaited journey into the sun's corona. As I noted at the beginning, we've looked at the sun in all different wavelengths, and you can find out an awful lot by looking at things in different ways. We've also sent spacecraft in as far as the planet Mercury, with, of course, the Messenger spacecraft and Helios 2 being missions that have gone quite deep into the solar wind, but not close enough to go into this sort of magic, the region where I like to say where magic happens, the region where we see this incredible heating and accelerating of the solar wind. And so that was what we needed to do with Solar Probe. Now, of course, it is challenging to do this with a mission. And so I wanted to go through some of the engineering challenges that we had with the spacecraft. It was always, nothing was easy with Solar Probe. Everything was always a challenge. And so we launched on a Delta IV Heavy. That Delta IV Heavy had an additional upper stage. And yet, despite all of that amazing launch capacity, we still had to be very, very light and compact. And so we would always say that the mission was always on a diet. You daren't put a pound on. So the spacecraft weighed 685 kilograms. That was the wet mass at launch. She's very small. She stands just 3 meters tall. The maximum diameter up there is the heat shield, and you can see that sort of the white surface on the very top there, and that's 2.3 meters in diameter. But the actual spacecraft bus itself is just 1 meter in diameter and a little under a meter and a half tall. So it was a big challenge to be able to fit all of the complex electronics inside. It was almost like a puzzle of, getting all of the different boxes and the different subsystems in there with a very complicated harness, a propulsion tank in the center, and everything in that very compact space. We wanted to be very light because we needed to have an incredible delta V when we left the planet. We wanted to make sure that we were not dragged around in any way by the angular momentum of the Earth orbiting around the sun. So we needed to leave any pull that the Earth might have on the spacecraft and really focus in towards the sun. So we wanted to be as light as possible to be able to take advantage of all of that delta V. And then we needed to be really compact because most of the spacecraft and most of the instruments actually kind of hide in the shade of the heat shield. And so you need to keep everything in and compact to make sure nothing violates the umbra and is in direct sunlight. So that was always a challenge for us. One particular challenge we had was the inclusion of momentum wheels on the spacecraft. So when we were first designing, it was thought we could do everything with little thrusters to keep the spacecraft attitude correct. The issue is, of course, then when you puff the thrusters, you're putting the plumes from the thrusters around the instruments, which means that they're measuring the plume and not the environment, which is, after all, why we're going there. And so we put momentum wheels in, which obviously can deal with most of the attitude control for the spacecraft. Every now and again, we have to puff the thrusters just to de-spin the momentum wheels. But instead of, you can imagine as we're screaming through the sun's corona, moving incredibly fast and sort of fishtailing through the corona sideways, there would be a lot of puffs in order to keep that spacecraft attitude. So we would not get any good waves measurements, electric field measurements in particular. So we changed to the momentum wheels. That was a big mass hit. And so there was a big study that went into doing that, but it was definitely a well worth the extra mass and the juggling that we had to do with some other subsystems on the spacecraft in order to really allow us to make those pristine science measurements. The biggest, I think, technology development, of course, would be the heat shield. And so there's a couple of different views of different aspects of the heat shield that you can see there. So in the middle image, you can actually see the assembly. That it was a titanium welded structure that holds the heat shield in place. And so that was done by a company that Tricor that had actually never really done any space business before. They worked with the nuclear industry, but they were actually the only company that said, oh, that sounds okay, we'll give it a go. We'll bid on this really, really complex structure. And they had their 3 best engineers and they were the only 3 that ever worked on this. So it was a real kind of almost like a part of the family when they came, the 3 engineers came to deliver the structure to the Applied Physics Lab where the spacecraft was built and integrated. So it was a real sort of pleasure to see them. I'm not a welder. I'm sure you're shocked by that. I'm not a welder myself, but I did see several engineers get kind of teary-eyed with the beauty of the quality of the welding on that particular structure. The heat shield itself is held in place on that structure by just 6 carbon bolts because we want the minimum amount of heat to be conducted into the structure. So there's just 6 small carbon bolts that hold the heat shield in place. It's not very easy to see on this particular one, maybe on the image all the way over on the left there. You can see under the black structure there's kind of little pie pan shaped structures. And that's how we bolt, that's where the bolts are. And they're almost like a shoulder joint. So they allow the heat shield to move on that assembly, because obviously as we go close to the sun, the heat shield will heat up and will change shape, may sort of puff up like a drum, may even kind of potato chip, look like a bit like a Pringle, doing these various different, as it goes hot and cold in the orbits. And so we want to make sure that the heat shield doesn't fly off. And so that was another very big technology development of just how were we going to keep the heat shield in place. And then on the top of the heat shield, there is a special coating, an alumina coating, and you can see that in the image all the way over on the right, with sort of a whiter than white coating that is a plasma sprayed alumina coating, which actually allows us to reflect most of the sunlight and not let the heat come into the heat shield. The heat shield itself is made of 2 carbon-carbon phase sheets. It's a bit like a graphite epoxy that you might find in golf clubs or a nice bike. So there's 2 phase sheets, very thin, and then there's a layer of carbon-carbon foam that is in the center of those 2 structures. And so that is the heat shield. And I'll just also note something I'm going to talk about in a minute, but on the left plot there, the sort of black fin structures that you can see, they are the radiator fins that we use for the cooling system for the solar arrays. And so that whole assembly there doing many, many different functions for us on the mission. So this is just a nice video, obviously a low-tech version. This is a sample that we have of the heat shield. And this is our thermal engineer, Betsy Congdon, who likes to do this experiment. So you can see it is glowing red hot on one side of the heat shield. Obviously in space, it's much hotter than this. And then ironically, that is actually a safety engineer who probably should know better, but is touching the other side of the heat shield and reporting that it is all nice and cool. And no heat coming through. It's also a nice shot there where I like this video is you can see the side view of the heat shield. So you really can see how thin those 2 plates, those 2 phase sheets are, and then that foam in the center, which is about 98% air. Again, all helping us to protect the spacecraft. And then just a shot here, this is actually in the thermal vac chamber of the heat shield. And again, you can see a nice view of the 2 phase sheets, the foam in the center, and then that white coating on the top. And you can see they're taking the assembly off it, and then it was going to go through its heat testing in the thermal vac chamber. Obviously, the spacecraft itself is in a region of about 3 million degree plasma, but the plasma itself is not very dense, so there are not very many particles. So even though the bulk temperature is up at 3 million degrees, there are not that many particles. So the thing we have to worry about most is the heat from the illumination, because we're so close to the sun. And so that's why that white coating is really useful, because it reflects a large amount of the sunlight. So even though we're in 3 million degree plasma, the front side of the heat shield gets up to about 1400 degrees Celsius. And the instruments or the main body of the spacecraft, everything on the main body of the spacecraft is at about 28 to 30 degrees centigrade. So a very nice, cool operating environment for the spacecraft, and that heat shield having to deal with those intense heats on the front side. Another big development for us was the solar arrays. And so we decided to use solar panels to power the spacecraft instead of an RTG. Now that may sound like an easy thing, after all, we're going to the sun, but as anyone knows who's accidentally left their iPhone on the front seat of a car on a hot day, electronics do not like to get hot, and solar cells are particularly prone to effects from overheating. So we have a very unique solar array. It's actually actively liquid cooled. So it operates under some extreme flux. And you can see there in the top panel, it's just, you can see a kind of close up view of all of the different, this is one of the main wings on the spacecraft. On the bottom panel there, you can see the sort of the last tip of the heat shield. And so if you can look at the diagram that's on the right hand side there, you can see the heat shield looks black. The solar panel looks black, and then there's kind of a little silver beveled edge that's pointing upwards towards the sun. That is that last panel down there on the left. That is our full-size solar array in the heliostat vacuum chamber, so being put up to really, really intense heat. And the tiny row of cells at the top there, that is the only row of cells that is illuminated when we're at our final closest approach. And so the entire solar wing is needed. All of those solar cells are needed when we're out around the planet Venus. But as she gets closer to the sun, she will actually, so she stretches out the solar wings as you can see here leaving the Earth, but anywhere where she's out around Venus. And then as we get close to the sun, tucking in those panels until just that knife edge of cells is sticking out. So that's the two ways that we keep the solar panels cool. One, by articulating them, and again, they're on kind of shoulder joints as well, so we can flap and feather them, either to put maximum amount of power in when it's cold out around Venus, and then tucking them in so just that final knife edge of cells is sticking out when we're close to the sun. And the same amount of power is generated from that one string of cells close to the sun as the entire wing when we're out around Venus. So this is just a nice sort of compilation of shots of us putting together the spacecraft. And this is a nice one because it shows you, I think, sort of how small the main spacecraft bus is. Here we are dropping in the main flight harness, and in the middle there with the pink cover, you could see the propulsion tank. So it kind of gives you an idea of just how little space is in there. There's the top deck. So there's that titanium structure with the radiator on it being lowered onto the spacecraft. And here they are doing the bonding for the heat shield. So you can see the carbon foam there being bonded onto that face sheet. This was the vibration test of the spacecraft. It was a terrifying test to witness. Anyone who's seen a vibration test knows what I mean. And then here we are lowering the spacecraft into the thermal vac chamber. This is actually at NASA's Goddard Space Flight Center, where we did all of the final acoustic and thermal vac testing on the spacecraft. Courtesy of the US Air Force, we took the spacecraft down to the Cape and installed the spacecraft at Astrotech. And here we're putting on those solar wings. Obviously, they've got a protective cover on them at this point. The last thing to go on solar probe is the heat shield. So the heat shield's lowered, and there you do see a nice shot of those 6 Pie-Pan structures. There she is in all of her glory. And then lifting the spacecraft to mate to the upper stage, that 3rd stage rocket motor that gives the really big kick of the Delta V. There is a lovely shot of the spacecraft in the fairing. So that's the fairing on the top of our Delta IV Heavy. If you look closely at the rocket, you can see at the top there a logo of Parker Solar Probe on the side of the fairing. And just for scale, the spacecraft in that logo is about the same size as the actual spacecraft herself. And so we were a teeny tiny little speck inside the Delta IV. But as I noted at the beginning, we really needed every ounce of the lift capacity from that enormous rocket to get us where we wanted to go. And so obviously I'm going to show this very beautiful image or sequence of images of the launch itself. And so this is August 12th, 2018, 3:31 in the morning, as in the very first second of the launch window, Parker Solar Probe lifted off to the sky. As we see the launch progress, moving now to an animation of the fairing opening and solar probe out in the atmosphere for the first time. 2nd stage motor fires, that's a cryogenically fueled 2nd stage motor, and then separation. And then you'll see that upper stage final kick motor fire once we're outside the atmosphere, giving Parker Solar Probe that final and very critical Delta V. There's spacecraft separation. Of course, the first thing we do is extend those solar wings to make sure we have power in the spacecraft. And then we started, it was a very busy 6 weeks to commission the spacecraft. We started to deploy the instruments. You saw the magnetometer boom coming out at the back. There are the plasma wave antennas on the front. I noted it was a really busy 6.5 weeks because in that time, Parker reached the orbit of Venus, and we did our first gravity assist around Venus. Now, Parker uses Venus to sort of slow down. We're moving incredibly fast, and we use Venus to sort of we give energy to Venus. We use it just to do almost like a little handbrake turn, to turn the spacecraft really in and focus the orbit into the sun. So you saw there a couple of sort of petal orbits that were being mapped out. Parker Solar Probe will do, you can see them here, 24 of those petal orbits during the lifetime of the mission. So the first Venus flyby was obviously right after launch, another 6 Venus flybys for the spacecraft during the prime mission, so that perihelion, or the closest approach, actually gets less and less, so we can get closer and closer to the star over that time. So I noted at the beginning that Parker's solar probe, well, the importance of Gene Parker, and so this was a very historic event. It was the first time that NASA had ever named a mission after somebody during their own lifetime. And so it was a real pleasure to have Gene with us and taking part in all of the activities up and around launch. And here there's just a nice shot of Gene when he visited us at the Applied Physics Lab. And I had the great pleasure of taking him into the clean room to actually meet the spacecraft that bears his name. And yes, I did say, Parker, meet Parker. And it was just a beautiful moment where Gene got really emotional and really choked up at just the sheer splendor of the technology that was in front of him, of this spacecraft that was going to boldly go and go into the corona and answer all of these questions. And so it was a very moving time for him, and also for all of our engineers, as he insisted on shaking them all by hand and thanking them for all the tremendous work they did to make this mission a reality. So I'd like to note, we're not particularly competitive or anything. We're just hotter, faster, and closer than anything has ever been. So for Parker, hotter, clearly we are operating in 3 million degree plasma. We are facing brutal heat and radiation. We are moving faster. We've certainly been breaking a lot of speed records as the fastest human-made object. On the last perihelion pass, we already broke a huge record. We are just about to do another Venus flyby. That's actually tomorrow. We will do our fourth of the 7 planned Venus flybys. And so that will set up Parker Solar Probe for her 8th and 9th close passes by the sun. And they'll happen in April, actually on the 29th of April, and then on the 9th of August. And after that, we will do the 5th Venus gravity assist, and closer she will go. During each of the passes, Parker Solar Probe will break her own record when she comes to approximately 6.5 million miles, or 10.4 million kilometers from the solar surface. And that's about a little under 2 million miles closer than our current orbit, or the one that we've just completed, perihelion number 7, when we were about 8.4 million miles, or 13.5 million kilometers above the surface. We will continue after we've done our 7th gravity assist. Parker will be hurtling around the sun at approximately 700,000, that's right, 700,000 kilometers per hour, or 430,000 miles per hour, which is about 118 miles a second. So she's pretty nippy at that point. And then at that final closest approach, she will be about 3.9 million miles from the sun's surface. So almost a little less than half the distance that she'll be on her next flyby. And so if you'll just indulge me, I really love this animation of putting the sun and the earth on either side of a football field, putting in a couple of familiar objects for scale. So you see Mars on the sun's 35-yard line, Venus on the Earth's 28-yard line. Some of those coronal loops that we saw in the initial movie at the beginning, they can get out to about the 15-yard line. So they really are standing proud from the sun's surface. Helios 2, I mentioned also as going inside the planet Mercury, or the orbit of the planet Mercury, that would be on the sun's 29-yard line. But if we put Parker Solar Probe into this, she will tuck and run all the way to the sun's 4-yard line. So quite literally studying the corona by flying right through it. And so I was asked to spend a little bit of time talking about the instruments before we get into some of the science results, which are very exciting. So this is the Fields experiment, and I'm going to show it to you where it is on the spacecraft. So we have 2 flux gate magnetometers and a search coil magnetometer that are on the back on that long boom. And then we have 5 voltage sensing electric field instruments, 4 on those long booms at the front of the spacecraft, and 1 is actually located on the magnetometer boom at the back. And that's really to help us remove the spacecraft potential and again, get those pristine measurements. I'm also going to note, because it doesn't show up on the animation, that on the next animation, but right, you'll see in the center there, sort of right hanging down from the heat shield. It looks like it's hanging down from the heat shield. That is the Solar Probe cup. That is part of another instrument suite, but it's a great view of it there. That is sticking out into the solar atmosphere. And so the Fields experiment makes direct measurements of electric and magnetic fields and waves. It measures Poynting flux, absolute plasma density, electron temperature, the spacecraft floating potential, and density fluctuations and radio emissions. So it really does a lot of different things for us to make our what we call our level 1 measurements, or our highest resolution measurements. The PI is Stuart Bale from the University of California, Berkeley. And for those of you who like graphs, I threw this together. This is the instrument capabilities. And so we're looking at the frequency. This is a log scale with the frequency of the various different measurements. And so, you know, we certainly knew that going in that the magnetic field was going to be a really, really key measurement for us. And so having both the DC and the AC measurements together means that we can cover a really big frequency range with a lot of precision. You can also see where the electric fields and the radio waves were, the sensitivity to those frequencies. We have 2 DC magnetometers, or 2 flux gate magnetometers, 1 inbound, 1 outbound, 1 sort of, in closer to the spacecraft and 1 on the very edge. And that is to allow us again to subtract any possible signals that are coming from the spacecraft itself. We can remove those by measuring it with the inner field, and then really get pristine magnetic field measurements. So the next suite is the SWEEP suite. So solar, wind, electrons, alphas, and protons. You can see the nice little animation here of rolling the spacecraft over. You see the 2 sensors. And then the third one I already showed you was on the heat shield, which is the Solar Probe cup. So the SWEEP investigation is measuring the velocity distribution functions of the most abundant particles, so the bulk solar wind. They're lower energy. It's basically what is always flowing with us in the solar wind. So it's looking at electrons, protons, and helium ions, and minor ions with mass per charge resolution. It's also looking at these bulk properties like the velocity, density, and temperature, heat flux, and phase space variations. Again, a lot of measurements coming from SWEEP. And so you see span A plus and span B. Span A plus measures both electrons and ions, and span B measures just the electrons. So when we put them on either side of the spacecraft, the fields of view of the 2 electron sensors fit together like the seams on a baseball, which gives us a 360-degree view of the electron population. That is really important because we want to look for counter-streaming electrons. That lets us know that we're on closed field lines. So the alpha particles, the protons in span A, we only look for those on the out, sort of going away from the sun, but the electrons, we're looking for them also reversing and coming back in towards the sun. The Solar Probe cup, I like to refer to it as the bravest little instrument because it takes no shade at all from our thermal protection system. It is sticking out, peeping around that heat shield out in the full solar environment. So it is a Faraday cup. It is a fairly simple instrument, but because of the very extreme temperatures that it has to operate at, it has to be made out of some pretty exotic materials. It has a little heat shield that protects a lot of the detector, but of course there has to be a hole to let the particles in, otherwise you're not going to measure the particles. So the instrument itself is made from, titanium, it's made with molybdenum, it's made with molybdenum, it is made with niobium, and all of the sapphire crystals that hold the wiring in place. So it's a pretty exotic instrument, even though it's a fairly simple instrument design. Then we'll look at this one, ESIS, the Integrated Science Investigation of the Sun. And so this is, you see here, it's two instruments. This is looking at the high energy particles, so things that are associated with those transients in the solar wind, shocks, coronal mass ejections, flares, anything that is causing a very high acceleration of energetic particles. So the ESIS suite makes observations of the energetic electrons, protons, and heavy ions, and they're looking typically at energies of tens of keV up to hundreds of MeV, and also correlating them with solar wind and coronal structures. The PI for that is Dave McComas from Princeton University, and there's a nice image there of that instrument, sorry. And then yet another graph for those of you who are interested in the energy. So I put the particle instrument capabilities against the energies. So you can see at the log scale there, again, the huge variation that we have, really covering the full spectrum of particle energies, going down to 1 electron volt when the spacecraft, at least when the spacecraft isn't charged, getting all the way down to 1 electron volt, and then up towards, not quite up to a gigavolt, but up to hundreds of MeV particles. And then last but certainly not least, our WISPR camera, the wide field imager for solar probe. And that is, you see a nice view there of the imager on the side of the spacecraft. Not a typical imager in the way that we expect to see, beautiful images of the sun. This pair of telescopes is really focusing on the solar wind. So it's looking at what is coming directly towards the spacecraft in the solar wind. So the telescopes take images of the solar corona and the inner heliosphere. They provide images of the solar wind. They can pick up images of shocks and other structures as they approach and pass the spacecraft. So this instrument really complements all of the other instruments on the spacecraft, because it's providing direct measurements by imaging the plasma that the other instruments are then sampling. So it's really helping, if you get these interesting structures in the particle data, you can add it with the image and really see, are you on a flux rope? Is it a big shock that's coming over you? What does the plasma sort of look like? And it helps us to really deconvolve those complex measurements that we're seeing. So now, without further ado, the thing that I'm most excited about is some of our science results. And so the first thing we'll do is, having finished with the WISPR camera, we'll look at some of the images. So this is viewing the solar corona up close. And so they're not particularly spectacular images compared to some of those that we saw on the sun's surface. But what is really interesting about these is they're taken really, really close to the corona, or really deep in the corona, I should say. And so you're seeing an interesting region. There's a little coronal mass ejection that comes out. But what's really interesting is these features are very small. And so we can't see them with our telescopes that are out around the Earth's orbit, or in, at the L1 point. By the time they get into a region that we can actually image from there, all of these features are kind of washed out. They've either been reabsorbed or you can't see them anymore. So there's this little, you can see that there, a coronal mass ejection, very, very tiny. So there's definitely lots of little tiny events that are going on that we've never been able to sample before. And then this is just another image of, or another movie of a particularly active, this is a one stalk of solar wind. And there's some interesting features in this one that we think we've made a discovery of magnetic field structures that were predicted, but never actually seen. You can't see it in this movie, but you can see it on the next slide. So magnetic islands have been theorized for years in numerical simulations. So we learned from these simulations that magnetic reconnection in current sheets leads to the formation of structures called magnetic islands. And these are sites where particles can be trapped and they can gain a lot of energy, particularly heat, as illustrated in that top panel of the MHD simulation. But however, this has remained a theoretical prediction for a long, long time because there was not much evidence for it in space data. But we believe that with that animation I just showed you, or the movie I just showed you, that WISPR observed a number of events that look like magnetic islands. And this is one of them. We see it forming along that stream stalk and moving outwards. And you can see it, it's the red dot with a little green circle around it. And so the importance of this new finding is really twofold. One, we're always looking for energy sources for heating and acceleration of the plasma. And so if there are these sort of little magnetic islands that are causing hotspots in the plasma, then that's definitely a possible heat source, and of course also an acceleration source. But also, if we are able to see these magnetic islands here, and this is still looking sort of fairly far away from the spacecraft. This was on a very early orbit before we'd started plunging much closer. So if we can see them this far away, then these magnetic islands should also occur all over the corona. So it was a really nice result to see something that had been theoretically predicted, actually see evidence for it in those movies. Second one, also a WISPR result, is there first evidence of a dust-free zone. So unfortunately, this movie is not playing very well, but our solar system is awash in dust. It's kind of the cosmic crumbs, if you like, of collisions that formed planets, asteroids, comets, and the other celestial bodies billions of years ago. And almost a century ago, Henry Russell predicted that there should be a region around the sun that is devoid of dust. And the reason for this is that the large dust particles far away from the star go through a kind of grinding process due to collisions. So therefore, the closer we get to the sun, the smaller the dust particles would get. And the small particles get heated much more effectively than large ones. So therefore, at a certain distance, these particles should get so hot to the point of evaporation. And so they're also subject to frequent collisions with solar wind ions. And so the evaporated material can get carried away under the effect of the solar wind and the radiation pressure, which therefore would result in a dust-free zone. And people have looked for this zone for decades, but of course you can't see it because you're looking through the dust. And so we've had to wait to get the imager close enough to be able to start looking for an area where we may have a dust-free zone. So with the next, oops. Oh, I have the multicolored wheel of death. Okay, give me a second. Hopefully the computer will not crash. There we go. So if we look at this movie here, it's not particularly clear, but you can see a sort of a decrease in the zodiacal light. So this is actually from the orbit 1, the first orbit data, and it's mostly dust scattered light. So if we plot the intensity of the light along the axis of symmetry, so the dashed lines there would be the intensity as seen from 1 AU, so as seen from here at Earth, and it increases all the way to the sun. And so that would mean that there was no signature of a dust-free zone. But if we look at the intensity that WISPR measured in the F corona, we see that F corona light starts to decline. It's a small change at the moment. As I said, this is from the first orbit. But it means that the dust density itself is also decreasing. And so this was our first hint that a dust-free zone exists. And so as we've moved closer and closer, we're seeing a larger and larger decline of the F corona during the closer orbits. And we expect to eventually see a full dust-free zone itself. And so we think that the dust-free zone will be a little more than 2 to 3 million miles from the sun. meaning that Parker could observe it as early as this year, when the flyby will carry the spacecraft close enough that the field of view of the imager actually will get down to that roughly 3 million mile area away from the sun. So we're really excited about that for this next orbit after the Venus flyby tomorrow. So another large discovery for us was these unexpected magnetic structures, which we called switchbacks, that are seen in the very young solar wind. So they're seen very close to the star. Now, as I mentioned when I was talking about the instruments, we knew that magnetic field was going to be the key to a lot of the various different phenomena. And so you see here a model. The red is the one polarity magnetic field, open magnetic field lines. Blue is the reverse polarity coming into the opposite pole of the sun. And you can see some sort of greenish yellow closed field lines there that are in the center around the equator. And so, you know, we certainly, with the spacecraft, we're in a region, we're coming in the ecliptic plane. And so we will see often regions of different polarity magnetic field, because as the sun rotates, we call it the ballerina skirt effect. The whole current sheet or the neutral sheet between these two polarity regions kind of twirls like a ballerina skirt doing a pirouette. So we know, you know, it certainly was possible that we could be seeing many reversals of magnetic field just due to the current sheet moving across the spacecraft. So we look at this plot. This is kind of a dramatic plot, the region not explored before. But so this is just we covered up the region of exciting data and show you that how far other spacecraft had got. So they just sort of seen the tips of this distribution. So now if I remove that, what you can see, of course, is just an incredibly dynamic magnetic field with a huge number of reversals. So you're looking at the radial magnetic field against time. And so these big spikes are actually showing reversals of the magnetic field. So of course, the first thing you do is check your instrument is working and this isn't spurious signals or noise on the signal. So no, it wasn't. And so then, you know, you start thinking, well, are we looking at current sheet reversals? Are we just seeing, you know, is the current sheet moving above and below the spacecraft so much that we're continually moving up into the different regions of the polarity? That's definitely a possible. But then we added the particle data to the magnetic field data. And so I'm not going to go through it. You'll be delighted to know this late on a Friday night. I'm not going to go through this in great detail. But if you look at the bottom plot, that is the electron pitch angle distributions. And so if you look at the top of that panel, you can see red in a number of places, and then a couple of regions at the bottom where you see intensity. So those are the reversals. That's the current sheet crossings. And so you can see one around maybe Halloween 1031 around here, and then we can see another one. This actually is a noise spike, and then there's another one over here and one here. So you know, you can see what 1, 2, there's another one, 3, 4, 5, 6, 7, but not enough to explain all of these wiggly lines or these big excursions here in the magnetic field. And so what it's telling us is that the plasma itself is staying on the field line. So it means that the plasma, it's not a big change in polarity where you're going from plasma flowing along a magnetic field line in one direction to plasma counter streaming on the opposite polarity. This plasma is staying in the same direction. So it's staying flowing across the field line. So there's no way that it is a current sheet crossing. So what it actually is the magnetic field is kind of reversing, flowing back towards the sun and then out towards the Earth or away from the sun again, causing kind of an S shape in the magnetic field. And this is just a nice graphic showing what this might look like. And so this is an unusual, very, very unusual. Did not expect to see this. And we actually saw this in our first orbit, so not particularly close to the star. But we saw a number of these S-shaped features. And so it's hard to put a kink in a magnetic field. It's a bit like trying to put a twist in a big, piece of rubber hose. You have to put energy in to do it. What the rubber hose wants to do is straighten out again. The solar wind clearly wants to straighten out. And so we have something that's causing these S-shaped curves in the lower corona, and then they are straightening out and releasing energy into the upper corona as the solar wind is flowing. And so this is just a graphic of what the data look like. But the important thing was we saw a number of these on our orbits that were further away from the sun. As we've moved closer and closer to the star, we are seeing both more of these events and also much larger in magnitude. And so here is a real possibility for an energy source for coronal heating. So really exciting result for us, a feature that we were not expecting to see. And then the final final science result I want to talk about is the discovery of an extended co-rotation of the solar wind. And so what I mean by that is here you can see a rigid rotation. So here you have a very strong magnetic field. It's orbiting with, or it's rotating, sorry, with the star. And basically as the star is spinning, the magnetic field is moving at the same rotation rate as the star. If we compare that to subrotation, which is what we know we have in the solar wind, so now the plasma is kind of being constrained. The magnetic field is loaded with this plasma, and it's sort of pulling, it's constraining the magnetic field, and so it's making that S-shaped, which we actually saw in the very, well, I think it was the second video when we looked down on the poles of the star, and you could see the solar wind kind of spiraling out from the sun. So this is what we expect to see. We expect to see the field lines forming this sort of weird spiral shape. So this is a prediction for where we would expect a kind of the transition from where we're seeing sun that is rotating or in that sort of the knee of the spiral to where it appears that the solar wind is moving radially away from the sun. And so one such question that we've really been thinking about is how exactly the solar wind flows out from the sun. Near Earth, we see the solar wind flowing almost radially, so meaning it's streaming directly from the sun straight out in all directions. But the sun is rotating and it releases this, and it's releasing the solar wind. So before it breaks free, the solar wind was kind of spinning along with the sun. And so that is causing this S shape. And it's a bit like a child riding a carousel. The atmosphere rotates with the sun, much like the outer part of the carousel rotates. But the further you go from the center, the faster that you're moving in space. Now, if you had you let somebody jump off the edge of the carousel, they would be moving then at that point in a straight line because they're no longer constrained by the rotation of the carousel itself. And so the solar wind then would not continue to rotate around, but it would then move radially outwards. I'll also call it kind of the garden sprinkler effect. And so in the same way, there's a point between the sun and the earth where the solar wind transitions from rotating along with the sun and flowing directly outward or radially, like we see from the earth. So for the very first time, rather than just seeing that straight flow that we see near the earth, Parker's solar probe was able to observe the solar wind while it was still rotating. And so it was as if Parker's solar probe got a view of that whirling carousel directly for the very first time, not just those children jumping off it. So Parker Solar Probe's solar wind instrument detected rotation starting more than 20 million miles away from the sun as Parker was approaching her perihelion point. And the closer we got to perihelion, the speed of the rotation continued to increase. And the strength of the circulation was much stronger than many scientists had predicted. But it also transitioned much more quickly than predicted from this spiral flow into an outward flow, which of course is what really helps mask these effects, these sort of edge effects from where we usually sit, even in as close as the planet Mercury, because that's not close enough to be able to see this transition. And so what we see there is just this radially flowing solar wind, but just a little bit in at 20 million miles away from the sun's surface, we're seeing this transition. And so this large rotational flow of the solar wind seen during our early encounters was a real surprise. We thought we would eventually get to see that, but we would need to be in at about 10 to 15 million miles away from the sun's surface. So much closer than 10 to 15 solar radii. Yes, solar radii away from the sun's surface. And we're seeing things happening at about 20 million miles away. So at incredibly much further out than we had expected. So a very exciting result from that early orbit. As we move in, of course, we are seeing this rotation and this transition on every single one of our orbits, and seeing the solar wind greatly accelerated and very much still rotating with the sun. Okay, and so I want to sort of finish by taking you to the other side of the heliosphere to see what's going on there. So it's the kind of, we're looking at with Solar Probe, we're looking at the birth of the solar wind. I want to take you now to the other side of the heliosphere, where we look at kind of the end of the solar wind. And so as we journey into the heliosphere, we can see there's a really nice shot of this protective cavity, this bubble that the sun, the solar wind is forming for us as we get to that region where interstellar space meets the solar wind. We've been able to study this because we were very fortunate that the Voyager spacecraft were able to show us not only tremendous views of the planetary flybys, but now really showing us how the sun is interacting with the stuff that fills most of the space between stars in the Milky Way. So this is just an animation of Voyager 2. And Voyager 2 is the only spacecraft to study all 4 of the solar system's giant planets at close range. It discovered the 14th moon at Jupiter. It was the first human-made object to fly past Uranus, and it discovered 10 new moons and 2 new rings at Uranus. It was also the first human-made object to fly by Neptune, where it discovered 5 moons, 4 rings, and the great dark spot. But it is now, together with Voyager 1, the furthest 2 spacecraft from Earth. So they were launched, 2 separate launches, but launched in 1977 and put into an extended mission following the completion of the initial mission in 1989. It was realized they could obtain really useful, groundbreaking, interplanetary, and possibly, we didn't know it at the time, but it was possible that they might get interstellar measurements of fields and particles as they were crossing the boundary. So it really extended the NASA exploration of the solar system beyond the neighborhood of the outer planets and into the outer limits of the sun's sphere of influence. The 2 missions have continued to characterize the outer solar system environment and search for the heliopore's boundary, so this outer limit of the sun's magnetic field and the outward flow of the solar wind. Voyager 1 actually crossed that boundary first, but we weren't quite sure that it had crossed it because it did not have a working solar wind measurement on the spacecraft anymore. So we could see the cosmic ray background pick up, but we could not see, we had magnetic field measurements, but we didn't have this really critical measurement looking for the solar wind to kind of die away. And so here you can see Voyager data from Voyager 2. It exited the heliosphere in 2018, and scientists were happy to announce that its 2 energetic particle detectors noticed dramatic changes. So the rate of the heliospheric particles detected by the instruments plummeted, while the rate of the cosmic rays, which typically have higher energies than the heliospheric particles, they increased dramatically and they remained high. And these changes confirmed that the probe had indeed entered a new region of space, which allowed us to say the Voyagers are both out. So they had both left the heliosphere, and you can see this graphic, Voyager 1 out on the northern lobe and Voyager 2 down in the southern lobe. And so you can see the position of them relative to the heliosphere, and Voyager 1 crossed the heliopause or the outer edge of the heliosphere in 2012, by the way. And Voyager 2 is still in the Helios sheath, or the outermost part of the heliosphere. So just a nice look at the kind of the full range of the solar wind, from its birth close to the star all the way out to its influence on the very edge of our solar system. And so I want to sort of wrap up by bringing you back to where we started, which is the importance of what we do. So in heliophysics, of course, we study the sun, but we study all of the impacts, not just on Earth, but all the way out to the very edge of the solar system. Here you see a nice shot of the Earth's aurora, the northern lights, caused by these very big, actually caused by the solar wind continually buffeting the planet. But when we see these really big solar wind events, these big coronal mass ejections, causing these very big energetic auroral displays. All of this energy coming into our neighborhood causes dramatic impacts to all of our technology. So the aurora, of course, causing issues for power grids, pipelines, undersea cables, anything long, and conducting. If the aurora is overhead and the ground underneath is conducting, then there isn't so much of a worry. But if the ground is not conducting, then those currents, that big current system in the sky, has to look for somewhere to close. Power grids, cables, long pipelines are all great places for energy to flow through, causing big impacts for those. Of course, we worry as we go back in our endeavor to put the first woman and the next man on Mars, and then onto the moon, and then onto Mars, and hopefully beyond. Astronaut safety becomes again a really, really high priority of making sure that we are doing accurate predictions of space weather to be able to protect our astronauts. Passenger airlines also affected by space weather, often when we get these big solar radio events, causing the polar region to become really absorbing. We call them polar cap absorption events, meaning that we can't actually get signals through those. And so planes either have to be grounded or diverted to avoid these regions. And of course, impacts to spacecraft. Big particles, big solar energetic particles can actually damage solar panels. They can cause spurious signals, single event upsets, all kinds of manner effects for our spacecraft. And we're now finding that there's a region where space weather from above interacts with terrestrial weather from below, causing kind of bubbles in this interaction region, which again will stop or really affect communications. And so GPS accuracy, all these type of things, the more we become reliant on technology, the more susceptible we are to the vagaries of the sun. And so I'll leave you with this sort of hurtling journey through the solar system, to remind you that NASA's Heliophysics division stands ready to study not only our star, but all of the space in between, as we endeavor as humans to continue with exploration to the moon, Mars, and beyond. And at that point, I will say thank you for your attention, and please keep looking up.
Thank you, Nikki. Great talk. Very interesting. We have time for questions and hopefully some answers. Our first question is Frederica Durema. Frederica, please unmute your mic and ask your question.
Yes, thank you so much for a wonderful presentation. A nice travel with Parker for us too, and all the experiments. Everything is very fascinating. I'm thinking a lot about the physics, but I have a question that may be mundane, but I mean, the instrument is collecting gobs and gobs and gobs of data, and how what's the rate, how they are transferred and things like that. Can you tell us a little bit about that?
Yes, certainly. So we do a sort of store and dump with the data. We have enough solid state recorder space for 2 full orbits. I mentioned everything is always challenging with Solar Probe, and the data downlink is no exception to that, because often we have a large glowing body, our star, that is between the spacecraft and Earth, and therefore we can't close the loop and be able to downlink the data. So we have to store it. And then whenever we get close to the Earth, we can close the link. And we use a Ka band downlinks. So we downlink at very high rates of data, but we do have to wait until we can close the link to be able to do that. So when it's good, we get high data down links. We are able to do our commanding on X-band. So we have X-band receivers on the spacecraft too. So we can use that for commanding. And also if we had to do like emergency housekeeping downlink, we can do that on the X-band, but it's just not a high enough data rate for us to be able to do it. So that's how we do it with Parker. She takes about 120 to 150 gigabits of data per orbit. We were able to increase the amount of data downlink. You put a lot of conservative margins in when you are doing the design. And when we got on orbit, everything was behaving really well. And so we have more than doubled that data rate. So now we're getting up to about 250 gigabits of data per orbit.
Yeah, one would think you collect terabytes and so, but I understand. Well, thank you.
Trust me, we would love to collect terabytes of data on every orbit, but the solid, it's again, having something that's hardened to be able to go into those atmosphere. We have a very hardened solid state recorder, and also just the mass of and the size of what we could put on the spacecraft. So I mean, we're really delighted that we're bringing down more than twice. Some orbits, if we can close the link really well, we can get maybe 3 times the original amount of data. So we're getting up towards maybe 450 gigabytes of data then. But yeah, we trust me, we would take terabytes if we could.
Yeah, thank you.
We have a question from Miles Taylor. Miles, can you unmute and ask your question?
Thank you very much for the beautiful information. I have a small question. All this magnetic field will disturb the communication of the probe to the receiving station. And the second question is, what is the life expectancy of that probe?
So we don't have to worry too much about the magnetic fields close to the sun, because literally we can't close the link at that distance. And also we're moving really fast. The other challenge, by the way, with downlinking is, that heat shield, which we like to keep between the spacecraft and the sun all the time, is often between, it often blocks the antenna. And so we have to be in a very particular configuration to be able to close the link and downlink that data. So we don't have to worry about the magnetic fields close to the star, because we're not downlinking data at that point. We're in full science mode. Then the life expectancy of the probe, this is like my heartbreaking question. I get it every time, will it burn up? Is it going to go into the sun, etc.? So it's a 7-year prime mission. And we, so that's, that's what the plan is, to do the full 7 years. That's 24 orbits, 7 Venus flybys. After the last Venus flyby, we are within the orbit of Venus, so we can no longer do that to get any closer to the sun, but it is a totally stable orbit. And so the probe will stay in that orbit forever until it runs out of fuel. So the fuel tank on board, I mentioned we have to puff the thrusters every now and again to despin the momentum wheels. At some point, we will puff our last puff, and there'll be no propellant left in that tank. At that point, of course, the probe will start to turn. And as she turns the side of the spacecraft, things that are not supposed to see full solar illumination, like the solar panels, like the radiators, like all the, any of the sensitive equipment, will then be exposed to the sun. And at that point, she will break up. And so she'll break first into larger pieces, and then, gradually, because of cosmic collisions and various other things, she will eventually be ground to very fine dust. And so I like to think romantically that she will orbit in the corona forever. She'll just become part of the corona. But we were very, very lucky, or I shouldn't say lucky, it was tremendous skill from ULA with that Delta IV Heavy. There is a trajectory, you want to hit the perfect trajectory when you leave the launch site. And there's always the tolerance, there's the plus and minus of where the acceptable range is. Well, they put us smack down the middle of that trajectory, which meant that we were able to cancel a number of the trajectory correction maneuvers that we would normally do out in the solar wind, particularly around Venus. When you're doing those Venus flybys, we often have to do little TCMs or correction maneuvers to really just fine tune the orbit. Because it was so perfect down that trajectory, we were able to cancel a number of those large correction maneuvers, which means we have more fuel. And so if we survive the intense heat and one thing I didn't note, another challenge is not just the incredible heat, but the fact that we're doing these petal orbits. And so we go close to the sun on one side and then out around the planet Venus on the other side of the orbit. So we have extreme temperature variation. And so if you think of any material, if you heat it and cool it, and you do that over and over and over again, most materials will change their property. They either become brittle and sort of flaky, or they can become plastic. But they really change their property. And so that's yet another challenge for us on Parker Solar Probe. So assuming everything is still working perfectly at the end of the 24 orbits, we should have enough fuel and enough stability to be able to do another number of years of operation beyond that, beyond the terrible day that we puff our last puff.
We have a question from Brett Magaram. He's a mechanical engineer, also a member of the General Committee. Does the Parker probe pass over the solar poles? And what latitude on the sun is it exploring? What have we learned about the sun at different latitudes?
Okay, so actually Parker stays in the ecliptic. So it was difficult to maybe see that in the video. I didn't have a really good one, but she stays down in the ecliptic. So she doesn't look at any different latitudes. The partnership that we have that is with Solar Orbiter, and Solar Orbiter will go out of the ecliptic a number of degrees and will allow the images to be able to look from a distance, but to be able to look down at the poles of the sun. And so we will do the in situ measurements of what's happening in that ecliptic region, which is where we see the big coronal mass ejections and the interplay between different speeds of solar wind. So one thing I didn't talk about was the open field lines, the open flux that come from the poles. That's associated with high speed solar wind, and the big coronal regions where you see the sunspots and the big coronal mass ejections, that's slow solar wind. And so that's one of the regions as well where we see this interplay between the two streams. So we're learning a lot in the ecliptic. We'll work with Solar Orbiter to see what they're seeing at the poles. But I will also note that we have one of the missions that we have in study right now is actually a mission to go over the poles of the sun. It's called Solaris. And it would actually go on a trajectory out to Jupiter, do a Jupiter flyby and kick it out of the ecliptic plane and fly over the poles of the sun. Another mission that went over the poles was Ulysses, which was an ESA-NASA mission, but that did not have any images on it. So it took in situ measurements and from a pretty high altitude. So the future goal of the Heliophysics division is to have a mission that will go fairly close to the sun's poles, both to take the imaging as well as the in situ measurements. And so to really get to your question of seeing how the latitude changes the effects we're seeing. So that's a future, what I like to call a stretch goal, because that will also require new technology development.
So I have a question that's more of a physics question. So it's true that the temperature is really high, but that's a measure of what the average kinetic energy of the particles, but the density of the particles is very low.
Yeah.
So how does that translate into the damage that's done? Is it from collisions with the surface? Is it from actual heat transfer? Because the heat transfer is low because the density is low, but the temperature is really high because the particles are moving very quickly.
So any damage that can come to it, I mean, you're absolutely right. And it's kind of counterintuitive because you say 3 million degrees and then you say the front side of the heat shield is 1400 degrees Celsius and everybody looks at you and go, what happened? But you're absolutely right. There's so few particles, there's very little heat transfer directly. Most of the heat we deal with comes from the illumination of the sun, the photons, the energy associated with the photons. Any damage done to the spacecraft, we would anticipate, although we hope won't. There's a lot of radiation, clearly, so you can get radiation damage, but there's a lot of dust. And so even though we're searching for the dust-free zone, we have to travel through a very dusty region, and there's a lot of very small dust particles. They're moving, they're hypersonic. And so even though they're tiny, they've got so much energy with them that they can do damage to the probe. So we did a lot of modeling of dust and the best way to protect things from impacts from dust. But that's our sort of the thing that we worry about the most, is that one large dust particle moving really fast that can do an incredible amount of damage.
I have a question from Rob Klein. What preparations are being made to reduce the impacts of a future Carrington event? And how is the Parker mission helping?
That's a great question. So there are lots of, I would say the preparations for it are really just understanding and getting better at predicting what is happening. And so, right now it's like you predict the weather. If somebody says it's a 10% chance of rain, that means 10 out of 100 times when they see conditions like this, you see rain. And so we're sort of in that area of prediction with the sun right now. If you see this big region and it's doing this, well, 10% probability, 10 times out of 100, that's going to explode and send a big event. So we're still in that region. The key that Parker Solar Probe will do is being able to sort of add the missing piece of the puzzle. What is the physics? So if you think of laying the sun and the earth out on a line and thinking about all the processes that occur between the sun and the earth that cause this Carrington-like events here at Earth, we understand the physics. We've made in situ measurements up to the planet Mercury, up until Parker Solar Probe. But we had this key region where all of these big physical processes that were happening that are causing not just the heating, but really the acceleration. What is causing these big events to erupt? And what is the physics? So when you do your global MHD models or whatever physics-based models you want to do, you need to know what physics goes into that key region. And so when you answer, these are the processes that are causing, or this is what's happening in this little bit of real estate on your Sun-Earth map, that makes the transformational improvements in our ability to predict. And so things like seeing these S-shaped curves, figuring out what's causing them, what their impact is, putting that physics, what physical processes are going on that cause those S-shapes, add that physics to those physics-based models, and that will make the dramatic changes.
I have a question from Bob Terry, a member, sponsor, and a physicist, I believe. Bob?
Has the probe shed any light on anomalous electron heating at the top of the solar atmosphere? This phenomenon where electron fluids abruptly jump to high temperature as they exit the denser part of the sun. Uncovered anything about what causes that?
I would say not yet, but we're heading in. I don't think we're quite close enough really to be able to do that yet. That is goals for later orbits as we're getting closer and closer. I have to say one of the really nice things about Solar Probe is there's almost like different campaigns as we're in different altitudes above the sun with those perihelion passes. So we haven't gone in to look at that anomalous heating yet, but that is one of our really main goals, is what is causing that anomalous heating.
It's been an abiding mystery for a long time.
It really has. And so those S-shaped, the switchbacks are definitely a heat source in there because you're getting a big energy release as that S-shape straightens out. But I would say right now we have some smoking guns, but we don't have a definitive answer yet. But we're getting there as we get closer. We need more data. And frankly, we've actually got more results early than we ever dreamed we would. I mean, we almost thought the first 10 or so orbits might be quite boring. And look at what we've seen in those, again, with just the solar atmosphere, the transition happening much further away from the sun than predicted, and all this activity much further out in the solar wind, the young solar wind extending further out from the sun. So we're definitely getting into the region, but we're not quite there yet.
Cool. Thank you.
A couple of questions from the web I'm going to read. Scott Matthews says and asks, I've read papers claiming that solar neutrinos may be the source of coronal heating. This seems far-fetched, but could neutrinos play a role? Would the Parker Solar Probe provide information on this?
We will not, we don't really measure neutrinos, and so it would have to be something associated with that, that might be a signal, or might be something that's associated, that you might say, hey, if we see this, then solar neutrinos may be doing the same thing. It's not something that we're going to look at directly. What I always love to say, of course, is it's science, so it's something we could do with the next mission, as you learn how to do these missions over and over again. And the Parker Solar Probe Mark II, with more instruments and more ability to do that, but we're not going to look directly at the solar neutrinos.
So I have a question here. What are the plasma wave detectors made of, since they have to be exposed?
Yes, good. I forgot to say that. So they are made of C103, which is a relative of niobium, and it's light, and so they're hollow tubes. And so the PI of the Fields experiment always gets really upset, because I always refer to the Faraday cup as the bravest little instrument, and he's like, hey, my antennas are out there too, But the Solar Probe cup is a big hunk of metal. I mean, it's a big, heavy instrument, and they're very thin niobium tubes, but they are they're able to withstand. Again, it's not just the heat; it's this continual change in thermal gradients. So that's what they're made of.
Yeah, there was a related question about the bonding of the reflective layer, aluminum reflective layer to the carbon, and whether there are problems maintaining the integrity of that bond because of the extreme variation in temperature.
Yeah, I sincerely hope not. It'll be a short-lived mission, and I'll be a very sad person. But it's actually plasma. It's plasma sprayed on. It's a very complicated process. It took, as you can imagine, a long time to put little tiny strips on it, because the other thing is not only is it hard, and you want to make sure that it's perfectly put on, but you also want it to be as perfectly flat as possible, to make sure that the heat across the entire surface is uniform and you don't have any hot spots. So it was done with a meticulous plasma spraying technique that took a long time to actually spray that on. But as I think I noted, the aluminum coating was actually specially made. It was designed and made for this particular mission, for this application.
So I have a question from Mike Houghton. Mike, get on mic. Unmute.
Yes, thank you, Nicola. This was a very beautiful presentation. My question has to do with predictability of solar activity. And will this mission draw us closer and closer to making some prediction capability? Just like the weather, it's kind of hard to predict, but there are some very good models that do good predictions. So will this mission help us along those lines?
Yes, for the reasons that I just kind of laid out, but it really by allowing us to add physics to our physics-based models in that sort of key region. And again, if you think of the sun and the earth on a line, we've been all the way into the planet Mercury up until now. And so we know what the solar wind looks like when it's radial and sort of when it's lost after all the magic's happened. And we know what the sun looks like, and we know how the sun operates up to a certain level. But really studying that low corona has just been the big sticking point. And so that's where all of the physics is happening that is causing the solar wind structures that in turn cause us to see the impacts at Earth. And it isn't just solar probe. Solar probe will make a profound ability, or, really increase our ability to predict space weather by adding the physics that of what is really going on that's causing the solar wind. So we'll do a better job of predicting, hey, we've seen something on the sun. Now by using our physics-based models, we can predict what it's going to look like much earlier, before it gets to our sentinels out at like 1 million miles upstream. But it really is, it's like a team sport. You can't do everything with Parker Solar Probe. I also need my spacecraft that are in the magnetosphere, that are in the ionosphere, thermosphere region, that are also looking at that sort of cradle to grave. So you're looking at the Parker Solar Probe will tell you how the solar wind is born, how it's initiated, and what big processes are causing the flow from the sun to the earth. But then it's also these spacecraft. We had the Van Allen probes that were in the radiation belts, really looking at how those big areas of radiation respond to different things in the solar wind. We have MMS, the magnetospheric multiscale mission, that is in the deep tail, looking at how the energy gets transferred from the solar wind over to the night side and then accelerated in, causing those beautiful aurora. And I've got loads of them. I'm only naming a few, but now we're doing a real focused campaign effort with a number of missions to look at the boundary between terrestrial weather and space weather. And we're seeing that terrestrial weather has an impact on space weather, and space weather has an impact on the high regions of terrestrial weather. So it's kind of putting this all of these sentinels together into one large observatory, and that's where we're really going to make the big improvements in our prediction, is by looking not just at how the sun is varying, but also how the Earth is responding to those variations in the solar wind.
Okay, thank you very much. That's very important. I might have missed this, but when did you say the first perihelion is going to be?
Actually, the first perihelion. So we've just completed perihelion 7. So the first perihelion, yeah, we are booking it. I tell you, in the solar wind. So the first perihelion pass was about 13 weeks after launch. So that's a pretty quick journey from the Earth to the sun. So it was in November of 2018. We launched in August. So it was in November of 18. And we've done 3 Venus flybys. Number 4 is tomorrow. And then we will head in for orbits 8 and 9 after that. So it's always busy on Solar Probe. We're moving fast. There's a lot to do. There's a lot of different maneuvers and things that are done. And of course, the challenge of getting our data down. And you can imagine the scientists are chomping at the bit every day for a few bits more data that they can see to start piecing this puzzle together. But yeah, the first one was in November of 2018.
Okay, thank you.
Got a question from Richard Gross on YouTube. Assuming we here on Earth are given 3 or 4 days lead time, what can we do to minimize the harmful effects of solar flares?
Okay, so 3 or 4 days lead time. So solar flares are actually harder because we don't get 3 or 4 days lead time for solar flares. The flares themselves are literally light, and light travels at the speed of light. So it takes 8 minutes for light to get from the sun to the Earth. And so when a flare happens, you only get 8 minutes warning that something is happening. And with a flare, and actually that's why there's a lot of honestly, there's a lot of research going on into how to predict a flare because you don't have that luxury. So I always think of there's 3 parts of a big solar event. There are 3 Ps. There's photons, protons, and particles. And so your photons are coming with the flare. They get there in 8 minutes. The protons, the very high energy solar energetic protons, travel at roughly, they can get up to half the speed of light. And so they get to the Earth in about 15 to 30 minutes-ish for depending just how energetic they are. So, if you see a flare, you've got maybe 10 minutes, 20 minutes to know that you've got a big particle event coming towards you. And so that's why we really do watch and predict if there's a big active region on the sun that would that we think could could erupt and could send out particles, then we don't want astronauts doing spacewalks or something like that at that point. You want them inside and protected. The particles are associated with the coronal mass ejection. So they're the big loops of plasma that you see expanding and exploding. They travel they can travel a couple of times faster than the ambient solar wind, and that's why you often see big shocks, like a sort of supersonic shock ahead of those. That's the event that we get typically about 3 days warning for. Fast moving events, you can get less than that. They can get to, you know, maybe a day and a half, 2 days. The Carrington event was about a day before they saw the effects to start at the Earth. So those you do have a little bit more luxury because you really can say, okay, we've seen the coronal mass ejection, it's coming this way. But at the moment, until it gets to the L1 point, that's where we can measure the magnetic field orientation. And if it's facing northward, it will have little impact on the Earth. It'll still, you know, cause activity, but it's not going to be a really big event. If it's a large southward field, that will be in the opposite direction to the Earth's magnetic field. Opposite poles attract. And so that's what lets in all the energy and gives us a really big space weather event. So there's kind of those three key things. But being able to predict a flare, trying to see signatures of what in that active region, what is going to tell us that flare is about to actually erupt is a huge area of science research right now.
But what can we do?
What can we do? So, scientifically,
Find a cave.
yes, absolutely. So scientifically, I mean, well, fortunately from a flare, we're not in any danger here on Earth because we have the atmosphere that protects us. It of course can affect our technology, and so there you harden technology. You know, you put coatings on solar panels. You harden electronics. You make them much more resilient to radiation. But scientifically, you want to get data that allows you to really know how to predict a flare. The other thing we can do to better protect us is which is another area we are researching, is looking at getting a stable spacecraft inside, like closer to the sun, so inside that L1 point, that million-mile point. And we actually have a technology demonstration that we'll be launching in 2025, which will be the largest solar sail ever flown. It's a CubeSat, but it will have I think it's 17,000 square feet, I think is the size. It's a huge solar sail that will unfurl in space and be used to propel and sort of hold the spacecraft closer to the sun than the L1 point. If that's successful, people have been dreaming of having these amazing solar sails that will, you can also use them to take you out of the ecliptic as well, to go over the poles of the sun, which was one of our first questions. So getting measurements closer to the sun give you more lead time. And so those are a couple of areas of research. So there's the technology, get measurements earlier, and then the science research. What are the smoking gun signatures that we can see, or what are the measurements that we need to make that maybe will tell us something big is coming? Radio measurements, by the way, you can get those ahead of the 3 days. They're radio signals that are produced by the structure itself, and there are radio signals that are produced by flares, and there are different radio signals that are produced by the massive blob of plasma. And the radio signals get to you before the blob of plasma. And so you can sort of chart the frequency of these radio frequencies and or radio waves, sorry. And the sort of steepness of the curve will also tell you how big the event's going to be. So there are a couple of ways that we're doing that. And we're also launching a mission in, I think, 2024, that is 6 small CubeSats that will go out into the solar wind and separate. And then they'll sort of talk to one another, and together they'll form like a giant radio telescope in the sky with these 6 little CubeSats. And that's going to make really great measurements of these radio signals associated with the big events. That's called sunrise.
So two last questions. One's a little bit fanciful. Have you learned anything that would be useful in people trying to develop fusion energy sources on Earth from all that you've learned about the plasmas in the sun?
I don't have a really clean answer to that. I mean, certainly we do fund work in lab plasmas in heliophysics to do that kind of thing, but we don't have an active program in fusion. There are other areas of NASA looking at nuclear fusion for this, but we haven't learned. I wouldn't say we've done anything close to that with Parker Solar Probe.
But I think the question really is, from what you've learned about plasmas in the sun, is there any information that will be helpful in designing fusion reactors here on Earth, since their primary, when I say objective, is to contain a plasma?
That's a great question. So, I mean, we learn a lot about how the star works, and it's a giant nuclear fusion experiment in itself is the star. And so I don't know how much it can be applied to the design of fusion reactors here, but certainly the comparison between the fusion experiments that are here on Earth with the nuclear fusion that's happening in the sun is a routine thing that we do. Like, you know, how are they related, and is there something different that's happening on the sun that we are not manufacturing here at Earth? That is something that we certainly do.
So the last question is, so I think the design of the spacecraft was based a lot on what you knew at the time about the energy distribution of the electromagnetic radiation and the particles that are in the solar wind and coming out of the sun. Have there been any surprises in the distribution of energies and particles that you found with Parker from what you already thought you knew?
I don't think so, not yet. I mean, so far the spacecraft is performing really well. We haven't seen anything that's anomalous. I mean, obviously you have little things here and there, but nothing that would lead us to say, oh, I wish that we designed it this way, or I wish that we'd done something different. So far she's performed as advertised in orbit. So nothing, no great surprises.
Okay. Final question actually came in from Robert Abramson. He wants to know, can a large solar event cause movement in the position of the Earth's magnetic pole?
And that is a really interesting question. And that's something that I've been thinking about recently. Maybe not quite in the way that you phrased the question, but what actually is fascinating me is if the Earth's, like, what would space weather look like during a pole reversal? You know, would you have quadrupoles? Would we have 4 auroral ovals? Would we have 8? Would we have 6? Like, you know, what would happen to space weather and during a pole flip is something I've actually been thinking about a lot. But no, it doesn't. It's not going to cause the Earth's poles to have a huge realignment. The Earth's poles are pretty stable. I mean, obviously they're wandering in the way they do over thousands and thousands of years, but the solar event itself it's not down in the base of the field. It's really out in the extended magnetic field, and so to really cause a big impact in the crustal magnetic field, you'd have to go much lower down to really impact it. It's really on the edges of the magnetic field where we're seeing the interaction with the space weather. But I am still fascinated about what space weather would look like during a pole reversal. It's my thing I'm pondering right now.
That's great. Someday maybe you can come back and tell us what it will actually look like.
Maybe I can, yes.
Thank you so much, Nikki. It was
Thank you.
great to have you here. It was a great talk. We really enjoyed it. And thanks for fielding all these questions.
Oh, it was my pleasure. Thank you so much.
Thank you. Thank you everyone for joining us. The recording of tonight's lecture will be available to everyone on the PSW Science YouTube channel and in due course on Vimeo and via the PSW Science website. Please share the links with your friends and subscribe to the channels for notifications on new postings. And please don't hesitate to join PSW. It's easy to apply for membership using the Join button on the PSW Science website homepage, and we really do want you to join. Before you go, we have a few important notes. The next lecture will be in 2 weeks on March 5th, 2021. The speaker will be James Spanson, project manager for the Giant Magellan Telescope. He will be speaking to us about the GMT, which will have approximately 10 times the resolving power of the Hubble Space Telescope, and when completed, will be the largest telescope ever built. We are pleased to note that PSW will mark its 150th anniversary on March 13th this year. Although we cannot meet in person then, stay tuned. A special event and gala celebration will be held to honor and commemorate the Society's sesquicentennial. The 2437th meeting will be on March 19th. The speaker will be Kate Kraft of Johns Hopkins Applied Physics Laboratory. She will be speaking on the Europa Clipper mission. The 2438th meeting will be on April 9th. Tentatively, the speaker will be Hod Lipson of Columbia University. He will be speaking on artificial intelligence, past, present, future. This will be one of several talks we'll be having on AI. The 2439th meeting will be on April 23rd. The speakers will be Simon Bennett and Dan Irwin of the London Crossrail Project. They will be speaking on the construction of the new Elizabeth Line subway, known as a tube to Londoners, cutting underneath London, sometimes with an arm's length of its loftiest skyscrapers. Additional lectures of the spring lecture series will be posted to the PSW website, www.pswscience.org. Check there often for updates. Last but not least, please join me in thanking tonight's crew for producing tonight's event: James Heelan, Ann McQueen, and Robin Taylor. Thank you all. And I will now adjourn the 2435th meeting of the Society. I wish everyone a great evening. Thank you for joining us. And with that, the meeting is adjourned.